All right, so just kind of as a reminder, the trigonometry. So, I know there's always some questions. It's like, well, why is trigonometry a prereq for this class? And, so why do we have to take that? So I just kind of want to talk a little bit or review a little bit about trigonometry here, and then um, just kind of show you a couple of things to think about that hopefully you at least discussed a little bit in there, but then we're going to see how that affects these three-phase systems that we're going to discuss. Okay. All right, so let's just kind of take a triangle here. So if we had a triangle, and of course I can't draw very straight, but let's say that we have this triangle here. So this is a right angle, and let's just say that these two um, sides are equal. I don't know. Let's just make them 1. Okay. So the horizontal one has a length of 1 and the vertical has a length of 1. And so using Pythagoras theorem, right, we know that the hypotenuse here is equal to 1 squared plus 1 squared. And then you take, well, so you say the hypotenuse is hypotenuse squared is equal to 1 squared plus 1 squared, right? That's Pythagoras theorem. So the hypotenuse squared would then, of course, be equal to 2, right? Or the hypotenuse then would be equal to the square root of 2. All right, and that's just Pythagoras theorem for a right triangle. All right, so but let me ask you here, if we know that the horizontal here is a 1 and the vertical piece is a 1, what is this angle right here? Do we know how many degrees that is? Uh, this is 90 degrees right here. This is the right triangle. Okay. Both sides are exactly equal. Okay, so if both sides are perfectly equal, then and you got 90 degrees here, then you're going to have 45 degrees there. Absolutely. Okay. All right. So if we kind of look at this on the other hand, let's say that the length of these triangles, instead of being 1, let's look at the kind of the exact same triangle, I guess, but make it a different length. So what I'm going to do is I'm actually going to make this 2. Okay. I'm not drawing it to the scale of the top one. I'm just saying here's a triangle with units, okay, of 2 and 2. Okay, and go a little bit higher, I guess, but all right, so this is still a triangle with 45 degrees here, 45 degrees here, all right, 90 degrees there. So now we're looking at, right, the height of the hypotenuse of this, okay, is going to be like 2 squared plus 2 squared, okay. And so that gives us, okay, let's see, 2 squared, 2 squared plus 2 squared, let's see, 4 and 4. So what's that going to give us? do math in my head this morning. So the okay. So yeah, it's 2.82, okay, which is actually, okay, if we look at that to see, so this is going to be 4 plus 4, okay, which is actually kind of, let's see, so we could have 4, 1 plus 1, which is going to give us 4 times 2. But see, we can take the square root of this, so this gives us 2 square root of 2, which gives us, as Josh put in there, 2.828. Okay. So, but I just kind of wanted to show you how, these square roots kind of pop up here. Okay. And so now let's take a look at one here that we have a length of, let's see, I'm trying to remember the number here off the top of my head. Let's see, I did this before class and then I done forgot it. The if we take 1/2, I think it's the square root of 3 in this direction, but when we go up this way, we're only going to go up 1/2. Okay. All right. So this here is a pretty common triangle that you see. This is 30 degrees here. Okay. Of course, it's a right angle here. So there's 30 degrees there and 60 degrees here. Okay. And so when you look at this now, the hypotenuse of this, all right, so we're going to have the square root of 3 divided by 2 squared plus 1/2 squared. All right, so when you square a square root, you get 3. And 2 squared is 4. And then when you square 1, you get 1, but when you square the 2, you get 4. Okay. And so when you look at this then, right, you got the square root of 4/4, which is equal to the square root of 1, which is simply equal to 1. Okay. So if this angle here is the square root of 3/2, and this angle here is 1/2, then we get an angle of, or a hypotenuse of 1. Okay. All right, so I'm going to do one more here. I'm basically just trying to get you familiar with being comfortable with these square root of 3 or square root of 2 terms here, because, or this, not, I mean 2 or 3, but the square root, right, is coming from the fact that we have to square, right? we have to square the each side. We have to square to get the hypotenuse kind of piece. Okay. All right. So here, let's take a look at one more. And so this one here is going to be 3/2. And this one over here is going to be the square root of 3 over 2. Okay. All right. And so now how did I get that? Well, you look at this here value and look at this here value. So if I take the square root of 3 divided by 2, and I multiply that by the square root of 3, okay, that's going to give me square root of 3 times square root of 3 is the square root of 3 squared divided by 2, right? So the square and the square root go, so that gives me 3/2. Okay. So you can see here, here's my 3/2. So what I did was I basically extended this line here. So instead of it being the square root of 3, I multiplied it by the square root of 3 one more time, and I extended it. Okay. And then I'm going to do the same for this side. So you take this side, the vertical side here, and I'm going to multiply it times the square root of 3 too. So, so this was the horizontal piece. Okay, so this was the horizontal. And so now what I'm going to do is I'm going to take the vertical side, which was 1/2, and I multiply it times the square root of 3. Okay. And so we take 1/2 times the square root of 3, and that simply gives me the square root of 3 divided by 2. So what I basically did here, so this was the vertical. Okay. And so what I basically did was I took this triangle here, or I took the triangle above it, right? And I just multiplied it. So I made it bigger by multiplying it by the square root of 3. Okay. So I just kind of made it bigger like that. Okay. Because I multiplied this side by the square root of 3, so that made it bigger because it was the square root of 3 divided by 2, so I multiplied it by the square root of 3, so now it's 3/2. And this side was 1/2, and I multiplied it times the square root of 3. So all I did was scale the triangle. So if all I did was take this triangle and scale it and make it bigger, if I scaled it evenly in both directions anyhow, and I just kind of made it bigger, then what is, if this was a 30-degree angle here, what is this angle here? What's this angle right here? Because I scaled the vertical and the horizontal sides by the square root of 3. So what's this angle? Dan, take a look at your last answer, right? It was 30 degrees here. When you scale both sides of a triangle, all you did was make the triangle longer. You didn't change the angle. So this angle is still a 30-degree triangle. All right. So if we have a value of 3/2, okay, what is 3/2 in decimal? Does anybody know? Got those big fancy calculators? Yeah, 1.5. Okay. So 3/2 is 1.5. And what is the square root of 3 divided by 2? Anybody know? Yeah, it's 0.866. Okay. All right. So, and the reason I'm kind of making a big issue of these is we're going to see these numbers a lot here. So let's just look at one more number here. What is the square root of 3? 1.7 something. I forget the rest of it. Okay, can you give me one more digit? 28 is 172832. Okay. Um, I I just wanted to remember for when we're doing intermediate calculations, you should use 5 digits for your intermediate calculations so that you minimize any round off when you go to your 3 significant digits. All right. So I just want you to kind of, so you're going to see like 0.866 pop up quite a bit, or you're going to see 1.73 1.732 pop up quite a bit here. All right. And remember, we're going to come back to this. All right. But just remember, if you have 30 degrees here, you're going to have, if you have 3/2 or 1.5 in one direction, and you have the square root of 3 divided by 2 in the other direction, that gives you this, this square root of 3, square root of 3/2 here, and the 1.5. All right. So let's look at the hypotenuse. I don't think I ever calculated the hypotenuse for this. So if this is my triangle, all right, so I've got 3/2 or 1.5 in this direction. And I got the square root of 3 over 2 in this direction, which is 0.866 to 3 digits. All right. But let's just do it in full boot. So the hypotenuse here, okay, the hypotenuse now is equal to 3/2 squared plus the square root of 3 divided by 2 squared, which 2 times, or 3 squared gives me 9, and 2 squared gives me 4, so that's 9/4. And then you got the 2 times, or squared, I'm sorry, this is a square term. Square root of 3 squared gives me 3, and 2 squared gives me 4. Okay, so that gives me 12/4, which gives me, if you divide 4, right, 4 goes into 12 3 times. And so this gives me the square root of 3. Okay, so the length of this hypotenuse now is the square root of 3. Okay. So, we're just, like I say, we're going to kind of come back to this because we're going to see this pop up here in a little bit. So if we look at, so this is, again, this is just trigonometry here. But what you're going to see when we start talking about these polyphase systems is you're going to see the square root of 3 pop up a lot. Okay. And so, why does it pop up? Well, it comes from this trigonometry, and it comes from this 30-degree phase angle here. Okay. Keep that in mind as we go back and we kind of look at these three-phase systems. Okay. So is there any questions about this? Again, this square root of 3 comes directly from the trigonometry. All right, so before we get into looking at the three-phase system, I want to kind of also discuss why we care. Okay, so here is this example that we kind of talked about last week, where we were powering the house. Okay, and I was talking about, in my house where I actually a couple of times had tripped my 100 amp breaker. Okay, so here is my 100 amp breaker. So I've got, and we're assuming just a nice even round 100 volts to make Mr. Monk happy, right? And so I've got 100 volts coming into my house, and I got 100 amps coming into my house, and that gives me 10,000 kilowatts. Okay, so, and we're ignoring transformers right now, so we're not, we're just saying that, ignoring the resistance in the lines that we talked about, and just talking about here, coming into my house, I've got 100 amps at 100 volts, which means I've got 10,000 watts coming into my house on 2 wires. Now, I didn't really talk about the second wire, but remember, if we're talking about electricity, okay, and if we're sending electricity from the power company here, all right, so if we're going to go from the power company and we're going to send 100 amps of current over to the house, it's got to return, right? So for electricity work, I need a complete circuit, okay? So if I don't have this complete circuit, I don't have electricity. Okay? So that means that if there's 100 amps traveling along this line here over to my house, then there also has to be 100 amps flowing back through, which means that I have to run 2 wires to my house to get this electricity. Okay, and so, and both of those wires have to be big enough that they can handle 100 amps. Again, for, skipping the transformer piece and stepping the voltage up. But, both of these wires have to be able to handle that much current. Okay. So they have to be very, very big wires. Okay. And to send that, and all I'm sending is 10,000 watts, which is, I mean, that's quite a bit of power, of course, but that's what I'm sending. So let's take a look now. If I go to a 3-phase system, okay, so if I go to a 3-phase system here, And so now, with this three-phase system here, as you can see, this is a delta connection that we're kind of showing right now. But if I'm actually generating electricity in a three-phase system, which is the way that we actually do it, and I'm sending this 100 amps into my house, okay, then it's going to have to come back through one of those wires, or maybe split and come down there. So we get 100 amps coming through there. All right. But at the same time, all right, remember this is a three-phase current. So at the same time, I could be generating electricity from here and sending 100 amps here and sending that 100 amps over this way and have it return through this line. All right, so if I did that now, I have 100 amps coming through the top. Okay, but now I just said that, wait a minute, I'm sending 100 amps through here, through this one. Change colors there. All right, so we're going to have 100 amps through here and returning back through here. And so here at this point, I had 100 amps going this way and 100 amps going this way. If they were exactly, 180 degrees out of phase, then that means I'd actually have, 0 amps on this line. Okay. However, if we come over and add one more, so let's say that I have, because now I've still got this guy sitting over here. So over on this guy, I'm going to send 100 amps this way. Okay. And send back over, right? And so if these were, again, if these were out of 180 degrees out of phase, they would cancel each other out. All right. But when we generate them, you see the way they're connected up here? They're not in phase, or they're not 180 degrees out of phase. All right. But what happens though is with these three wires, I can send, I'm effectively, let's just say I was sending 100 amps through each one of these. So over here, instead of having 100 amps, I actually have 300 amps. Okay. So I'm actually getting 300 amps, or 3 times the amount of power. Okay. I can get like 3 times the amount of power delivered over here to my house by connecting one more wire. All right. So, because up here I had 2 wires and I was getting 10,000 watts. Okay. So now I've got one more wire. So I run one more wire and I get 3 times the amount of power. I'm getting 30,000 watts. Okay. Or another way to look at this is the wire doesn't have to be nearly as big, because if all I really need is 10,000 watts, then these wires, since with using the 3 wires here, I can reduce my current. Okay. So I can basically divide my current in half. So I only need about 33.3 amps of current to flow with these 3 wires and in each kind of wire. Okay. So I can reduce my wire by the size of my wire, because I can reduce my current by basically 2/3. Okay, so instead of having 100 amps, okay, I'm reducing that by 2/3 and I'm just getting 1/3 of the amount of current for the exact same power. And so when we talk about like the, when we think about there is resistance in this wire, and we talked about that huge loss due to that resistance, if I can reduce my current by 1/3, then I'm going to significantly reduce the power loss here. So by running just one more wire, I can either triple my power or reduce my current by a factor of 3. Okay. And so either one of those, is a huge gain. So three-phase power is very, very convenient. Okay. Because you need two wires. No matter what you do, you have to have two wires to get electricity. So, so you've already paid for these two wires. All right. And so if you pay for this one extra wire, you can actually triple your power by just adding one more line, or you can reduce your losses and reduce the size of the wire. All right. So if you reduce the size of the wire by a factor of 3, you save a lot of money there. Your wire is a lot smaller. And so you save money by reducing the wire to get the same power we were sending for two wires. Okay, so it's highly possible that, if all you're looking for is this 10 kilowatts, then, but you're reducing your wire, this wire here and this wire here, you're reducing it by 1/3, then, but you added an extra wire. Okay, but you're reducing how much current, so you're reducing the size of the wire. Okay, so you don't need such big wire because, so it may actually be cheaper to run the third wire, run 3 wires that are much, much smaller, would actually be cheaper than to wire these 2 great big wires, right? Because the size of the wire would be smaller, the weight of the wire would be much, much smaller, which means that your towers that are holding the wires up can be smaller. So any way you look at it, it's just hugely beneficial to go to a 3-phase system. All right, so I just, I kind of like to give you this example here so you see why we care about 3-phase. All right, so is there any questions about that? All right, so we talked about why we care about 3-phase, all right? And we talked about looking at this triangle here and looking at this right triangle. So this is a right triangle here with a 30-degree and a 60-degree phase angle here. And so we saw, like, if we end up with a value of 1.5 in the horizontal direction and the square root of 3, which was 0.866 in the other direction, all right, then we end up getting our hypotenuse. We end up getting a hypotenuse with a square root of 3, okay? And so basically, that's increased that value. All right, so let's take a look here at how to wire up a 3-phase system. Okay, so if we're going to use 3 phases, okay, we've already kind of talked about delta to Y conversions, right? We talked about them in DC, and we also talked about them back in chapter 18, I think it was, and how to convert between those and whatever. So we're going to kind of look at those differences here in a little bit. But let's just say that, if we take an AC circuit, All right. So I have an AC circuit going here. And so this is just one, and let's just say it's 1 volt, angle 0 degrees. All right. And so we're going to feed this into a resistor here. Right. So here's a nice simple circuit with just one voltage source. Okay. All right. So now, if we look at a circle, okay, so if we look at a circle, we know that the circle is 360 degrees, right? So to go completely around this in degrees, we're going 360 degrees. So if we're going to build a three-phase system, we want to be able to split this evenly, okay? And so therefore, you know, we're basically trying to split this piece of pie here up evenly. And so to do that, we would have to have angles, right? So you take 360 divided by 3. So that would give me 120 degrees, okay? So to build a three-phase system and make it as even as possible, we want to be able to split it up in threes. And so that will give us a system that kind of looks like this here. Okay. All right, so this is going to be a Y system. I'm actually, I guess, kind of going to draw it a little bit upside down here. All right, so, but this is my three-phase system here. And I'm going to connect this in a Wye connection. And we're going to come over here and I'm going to run it into that wasn't a very straight there. Okay, so we're going to connect it into a Y setup of resistors here. I'm going to use a different color here for this so that it all right, and it doesn't really matter there, but you know, and this is ground here. All right, so since this is ground, those are connected. So if we look at just the top circuit here, so if we look at just this top circuit, right, this is actually pretty much the exact same circuit as I had up here. Okay. But then I've got 3 of these. Okay, so I've got 3 of these circuits here. And so this is a kind of a Y connection here. And the nice thing about Y connection circuits like this is that you do have a ground connecting them. Okay, now you don't necessarily need to have that ground connected, because the current, if you're passing current through here and you don't have the ground, so if we actually were to say remove this ground on one or both sides, so now we don't have that ground, but the current can still return back to the source it came out of. Okay, it can either go through this path or the current could go through this path, but either way it's going to end up coming back to this power source. All right, so if this is my power source, right, I can have this current flow, and it can come flow through this way and flow back, and it can come back and flow through this way. So either way, without the ground, if I didn't connect that ground, I'm still going to have that current flowing back and returning to my current source. So I have a complete circuit. The nice thing about having the ground is that if the system is unbalanced, so that if one of these resistors wasn't exactly 12 ohms, it was only 9 ohms, okay, then by having a ground here, it gives an extra path for current to flow. All right. It also gives a path for like noise injected into the system or something for it to flow. All right. So, but looking at our power supplies here. So I've basically got a generator. I'm going to generate electricity. Okay. And I'm going to, so I've got one generator, and I've designed this generator such that it's got 3 different coils, and each are 120 degrees out of phase. All right. So then this is going to be a voltage. We'll call this E1, call this one E2, and call this one E3. Okay. And so if E1 has a voltage of 1 volt at an angle of 0 degrees, okay, then E2 is basically 120 degrees behind that. So E2 then is going to be 1 volt at an angle of minus 120 degrees. And then E3 would be 1 volt at an angle of plus 240, or excuse me, minus 240 degrees. Okay. However, if you look at a circle, okay, and so you're going from here, this is my reference, and if you're going minus 240 degrees in this direction, if you look at it this way, it's plus 120 degrees. All right, so this minus 240 could also be written as plus 120. So we have this one is trailing. You could kind of say that E1 is trailing, or E2 is trailing E1 by 120 degrees, and E3 is actually ahead of E1 by 120 degrees, right? So the whole idea here is because we have a circle, and a circle is 360 degrees, and we want this to be balanced. So we're doing 3 phases, and we want them balanced, and so therefore it's going to be 120 degrees phase shift. And so, so it doesn't matter really which one of these that you select to be your reference point, but one of them, if you call one of them 0 degrees, then the next will be minus 120 degrees, and the other one would be plus 120 degrees. All right, so given that, All right. Let's look and, let's think about Kirchhoff's voltage law for a minute. Kirchhoff's voltage law says, well, if I don't have this ground connected, but Kirchhoff's voltage law doesn't care about ground. Kirchhoff's voltage law says that the voltage around a loop is equal to 0. All right. And so you can pick any loop you want here. So it doesn't matter which loop you choose. All right. But so you go around here and you return, right? You've went around the loop. Okay. So if that's the case, then you're going to have a voltage drop here. Call this resistor R1 and R2 and R3 or something. Okay. But when we do Kirchhoff's voltage law, notice the plus signs. I put plus signs up here. Okay, the plus signs, see, I've got this ground connected here, right? So the plus sign, I've got the plus sign. The positive of the source is connected on the opposite side of the ground for all three of these. Okay. Just raise it up just a little bit more here. All right, so if we look at Kirchhoff's voltage law, then we have that we go around the loop, we're going to have E1, right? So we're starting here at ground, we're going to go up, so we see that we went up E1, so that's a positive E1. And then we're going to come over here, there's going to be a voltage drop across this resistor, so that's going to be a voltage drop, which is going to be a minus VR1. And then we're going to have a voltage drop here, so that's going to be a minus VR2. And then we're going to come through here over, and we're going into the plus and coming out of the minus of E2. Okay, so that's actually going to minus E2 is equal to 0, right? And this again is just Kirchhoff's voltage law. All right. And so if we look at just E1 and E2, so if we look at the voltage across here, that voltage is E1 minus the voltage E2. And so if we draw a phasor diagram for that, all right, we have E1 is 1 volt at an angle of 0 degrees. Draw it a little bit larger here. So we have E1 is 1 volt at an angle of 0 degrees. Okay. And E2 is 1 volt but at an angle of minus 120 degrees. Right? So this was E2. And this was E1. Okay. And so they both have the same magnitude, right? Because we're generating them actually within the same thing. So they're designed so that they're both going to have the exact same magnitude. So we have this one here, which is at an angle of 0 degrees. Okay. And let me see if I can change the color of this. Just probably not. And I can't easily change the color of all of it, but yeah, that's what I thought. All right, so this is E2 over here. Okay, now, but E2 is at an angle of minus 120 degrees. Okay, so that's going to be 120 degrees. All right, so E2 is connected this way. Okay, to move this down a little bit. So, all right, so they're both the exact same length. Okay, and so if we add these two together, okay, so if we were to add them together, we would add it this way. However, we're not adding it, we're subtracting it. All right, so we are subtracting over here, right? We are subtracting, that's a minus sign there, right? We're subtracting E1 minus E2. So when you subtract it, that's a 180 degree phase shift. So now if this was my E2, okay, I need to actually rotate this 180 degrees. So it's actually going up in this direction. Okay. And so it's going up that way. And so now if I was to draw this triangle, okay, so we have over here, right, this is E1 right here. And this is E2. It's actually not E2, it's actually minus E2. Okay. So this is minus E2. So E1 minus E2 is equal to this value right here. Now, remember that the length right here is a length of 1. Okay? So this is a length of 1. And if we were to drop a line right here, this would be a right triangle. And what you're going to find out if you were to measure this, okay, so this line right here is 1/2. So we have 1 plus 1/2. Well, gosh, 1 plus 1/2, that gives us that this length, this entire length here, turns out to be 3/2. No square root. I don't know why I wrote that. This entire length is 3/2, and this length over here turns out to be the square root of 3/2. All right, and so we were looking at this triangle up here earlier, and we saw that if we have 3/2 and the square root of 3/2, then we get that this hypotenuse we get that this hypotenuse ends up being the square root of 3 volts. All right. So if my voltage here was 1 volt, then when you add E1 plus E2, the magnitude of that voltage is the square root of 3. And the phase angle of this, remember the phase angle was 30 degrees. All right. So that's why I spent that time talking about the trigonometry piece. So when you have this circuit up here where you have 3 voltage sources connected in a Wye connection like this, you have a voltage, okay, you know, we call this like a phase voltage. Okay, so E1 is what we call a phase voltage. Okay, and E1, you know, is aligned to neutral, right? So this was my ground. This is connected to ground. So this is called a phase voltage. Sometimes I'll write it like V phase. This is one phase. And so this one phase, okay, which is aligned to neutral. So it's going from here to neutral. And if it had a magnitude of 1, right, so if its magnitude was a 1, when I measured the voltage from here to here, so if I put in a voltmeter and I measure from here to here, this is what we call a line-to-line voltage. And I measure the voltage from line to line, and from one line to ground, for one line to ground was 1 volt. Line to line is going to be square root of 3 bigger than that, and it's going to be at a phase angle of plus 30 degrees. Okay, so this is the change when I look at just this 1 voltage here. It was 1 volt angle 0 degrees. When I measure the voltage from this line to this line, it's the square root of 3. So it's bigger by the square root of 3. The voltage is bigger, and the phase angle is shifted by 30 degrees. And that's what this Phasor diagram here is showing me. Okay, so I have a 30-degree phase shift from E1. Remember, E1 is the magenta sort of color here. So here was E1. All right, so this was E1 right here. And so this is bigger by the square root of 3. And it's got a 30 degrees phase shift. So it's actually ahead of this voltage. All right. And then if we looked at the other 2 lines, we would kind of see the exact same thing going on there. So we would end up getting, you know, when we look at this, it really got, my drawing gets so messy. But when we look at this, okay, you have these line voltages. I don't know, let's call them like line A, B, and C. Okay, usually they use these references here. So, all right, so if we look at, say, this is line A, and this is line B, and this is line C. Okay, so when you look at these 3 lines, A, B, and C, then you can say that the line voltage, VA to neutral, right, was 1 volt angle 0 degrees. And VB to neutral was 1 volt at an angle of minus 120 degrees. And VC to neutral was 1 volt at an angle of plus 120 degrees. Okay. All right, so now if we were to look at line to line, we were measuring the voltage VA to B. That's what I have up here. That's what I'm showing right up here, right? Was the voltage VA to B, which is equal to VA minus VB, okay, is the square root of 3 at an angle of plus 30 degrees. And then the voltage VB to C, okay, is VB minus VC, which ends up giving me the square root of 3 at an angle of minus, okay, it's a 30 degree phase shift, so it's going to be a 90 degrees. And VCA is going to be VC minus VA, which is going to be the square root of 3 at an angle of, we have 120 degrees and we're adding 30 degrees to that, which would be 150 degrees. Okay. All right, so these over here are line to neutral voltages. And these ones over here are line to line voltages. Okay, so the line to line voltage is going to be larger than line to neutral voltages by this square root of 3 value. Okay. And they're going to be ahead of those by 30 degrees. Okay, so there's going to be a 30 degree phase shift. So if you were to measure what we're basically doing is looking at measuring the voltages. So if we're measuring the voltage line to line, we expect it to be the square root of 3 bigger than the line to neutral. Okay, so if you were just measuring it to ground here, or you're measuring it from line to line, there's going to be a square root of 3 piece comes. And that comes from the Phasor diagram. That comes from Kirchhoff's voltage law and doing the trigonometry. All right. So we've added E1 minus E2. And then when we look at that as a right triangle, so here's my right angle over to here. Okay. And so this was my right angle. Then we end up getting this 3/2 in the horizontal direction and the square root of 3/2 in the vertical direction, which gives us that square root of 3. So that's why you see in the three-phase systems, you see this square root of 3 popping up. It comes from this trigonometry piece. Okay, and it comes from Kirchhoff's voltage law, adding these up, because you're measuring a voltage here through this phase minus the voltage through the other phase, which is giving you a line-to-line voltage, right? And so that line-to-line voltage is the square root of 3, and then there's also, it's going to be 30 degrees ahead of your reference. Okay, so in this case, I was using phase A as my reference, so I'm 30 degrees ahead of that. All right, so Josh, when you add all the line to line, it becomes 0. Yeah, or you add the line to neutrals. Okay, so it really doesn't matter. Oops. There, you know, if you take these, let's look at these here. Okay. All right, so we're going to take the line to neutrals and add them all together. Okay, so we're going to take the line to neutrals. We're going to add these all together. So I'm going to take so this is going to be VAN here. Okay. And I'm going to take this here, and I'm going to add this up. Okay. So I'm going to rotate this, right, by 120 degrees. Okay. And I'm going to throw it in there. Okay, so that's right. So shoot. Let's see. Let me set this over here. So this is and then let me make another copy of this. Okay, and I'm going to rotate this one by 120 degrees in the other direction. All right, so these are my 3 values here. So this is the first one. I'm going to just label them here. And this is minus 120 degrees. And this one over here is plus 120 degrees. Okay, so I've used the software here now to rotate these. So each one of these are just the voltages, right? This is 1 volt angle 0. So that's angle 0. It's going perfectly horizontal. This is 1 volt, but I rotated it minus 120 degrees. So it's going minus 120, which is down here, you know, and, you know, when you look at the Y, it's going down. Okay. It's, you know, so here is my thing, and then this would be a 120 degree, right? As we rotate this minus 120, where it's rotating over there, so that's minus 120 degrees. All right, and then this one over here is rotated plus 120 degrees. And so now I'm just going to add these three together. Okay, so I'm going to just select them, and I'm just going to take this one here, and I'm going to then take this one over here, and I'm going to add it. I'm just adding it to the tip of the first one. And then this one here, I'm adding to the tip of the second one. So this one here, what I've got here is simply, I've got VAN plus VBN, B to neutral, plus VC to neutral is all equal to 0. Okay, those three add up, and this was line to neutral. So now let's come up here and take these three. Okay, so we'll take these three over here. Oops, guess I didn't copy them. Line to lines. So here are those line to lines. And so I'm going to take the first one. All right, so this is the square root of 3. Okay, so this first one is my reference. Okay, so I'm just taking this here so I get the length correct. All right, so now I'm going to take this and I'm going to rotate this 30 degrees. Okay, so that is this one over here. Okay, so these are the line-to-line voltages. Then I'm going to take this one here. I'm going to copy it again. I'm going to rotate this one minus 90. Okay, so there's that one rotated minus 90. And then I'm going to take one more copy of it. Or I guess I can just take it now. So they're all the same magnitude. Okay. And so this one is going to get rotated 150 degrees. Okay. All right. So there's my first one. Okay, so we're going to go from there. We're going to tap that one right in here so it adds up there. Okay, remember, these are all the same length because I copied them. And this one's going to go right there. All right, so this one here now is V A to B, and I'm using lowercase here just so it'll work in the text. Okay, so hopefully that doesn't throw you off. But this is VA plus B. So, you know, VAB, that's this 30-degree one up there. And then the next one is VBC, which is square root of 3 minus 90. So that is BC. And then we're going to add, okay, these are all plus signs here, CA, and that is equal to 0. Okay. So it doesn't matter whether you're adding line to neutrals. Okay. It doesn't matter whether you're adding line to neutrals or you're adding line to line, when you take the first voltage and you take the second voltage and you take the third one and you add them all up, you get nothing. Okay. So if you take all three of those voltages and were to add them up, you get back to zero. Okay. Now that doesn't mean that we don't have voltage there. Okay. It just means that they are out of phase with each other. So what are we doing? We're going around the circle, right? I mean, this is a 300. I'm trying to get a good circle out of this. Doesn't look too good, but all right. This is a 360 degree. It's rotating, right? This thing is like rotating around a circle. And so, as you go around, it's just like the sine wave, right? It goes around. So when you add the three together, you're always back to zero. It's Kirchhoff's voltage law. Okay. You're going around a loop and you're getting back to zero. Isn't that weird how things like that work? Okay, so, but, I mean, when you think about everything we've done this semester, Kirchhoff's voltage law, Kirchhoff's current law, Ohm's law, they always apply, right? And when you can do mesh analysis, okay, or nodal analysis, those are all going to work. It doesn't matter whether it's a one-phase system or a three-phase system, or, you had a 12-phase system, okay? Kirchhoff's voltage laws and Ohm's law are always going to apply. Okay. And so none of that breaks down. So, when you have a big complex circuit, so when you start looking at these circuits, they can definitely start looking a little complex because you've got three power supplies and you've got this connection here, right? Here's the kind of the circuit, which kind of got messy, but this is kind of a standard. This is a Y to Y connection here. Okay, and you can have a Y to delta, delta to Y, delta to delta sort of connections going on. But, you can always apply mesh analysis to this, okay, and solve it. Okay, but I mean, a lot of times we're talking about with these three-phase systems like this, we're talking about power kind of systems. And so, what we're doing is we're hooking a three-phase system up to usually something like a three-phase motor. And so the three-phase motor, as much as possible, are designed such that they're all three the same. So if it's 10 ohms and if it's 10 ohms up here, it's 10 ohms here and 10 ohms here. I mean, unfortunately, they're always going to be off a little bit. One might be 9.8, one might be 10.1. Right? But they're going to be close to being balanced. Okay. And if they are balanced, a lot of times what they do is they do, like when they draw these, they draw them, instead of drawing like all these wires going, they draw them as what they call one-line diagrams. Okay. So I put some slides out there in Blackboard. You guys have probably already looked at them, but I just want to kind of go over and go through some of these slides. Now, there's quite a few slides. I'm not going to go through all of them. I'm just going to pick a few of them to highlight here. All right, so, and I kind of talked about this when we were talking about the transformers and stuff, but when you look at these transmission towers here. Okay, let me just trying to highlight this on the screen for you. Okay, and all right, so but when you look at this, you always see these towers are laid out in a manner like this. Where they're in sets of 3, right? So they're wired up here in sets of 3, okay, because these are 3-phase systems. And when we look over here, right, here's a transformer. Here's a transformer with 3 phases, okay? All right, and so here's just a graphic here. It's with a little animated GIF showing you the single phase system, and it's just kind of mapping as the rotor inside of the generator rotates, it's generating a sine wave, right? So there's a single sine, and so it just, as it rotates around the circle, right, we get our maximum and then our minimum there. And so that's kind of a nice little graphic. Now here is showing 3-phase, okay, and a lot better drawing than I had earlier, all right? But here's a 3-phase. So we have here this these 3 phases, and these things are, 120 degrees apart, so that they are perfectly matched around the circle, right? So we have a circle that's 360 degrees, and so we're going to space these 120 degrees apart, so each one of them has equal spacing. All right, so given that, here's another little animation. Where was it? There it is. Okay, so this is a really, really, really nice animation, I think. It's showing you the 3-phase. This one here is just kind of trying to show you the 3 different phases as they rotate around. They're generating as the actuator now. It's actually got 3 coils in here, so it's generating it, and they're just rotating around there. Okay. And so you can see that these sine waves are being generated, but each sine wave is 120 degrees out of phase with the next one. All right. And then this one here, this top one here, I can't seem to select it here. Okay. And I think it's got a transparent background, so I can move these guys out of the way, so just make this a little bit bigger so you can see this. But this top diagram here really is nice because it demonstrates how the currents are flowing. Okay, so you can see, the red is kind of trying to show you phase 1. Now notice these are actually Wye connections, but there's no ground. All right, so as I said, it doesn't really matter. You can build a generator, you can build the load either in a Y or a delta sort of connection, but you don't have to have a ground. And if the system is balanced, you don't gain a whole lot from the ground, because you could run that 4th wire as a ground wire, but if the system is perfectly balanced, the ground wire will never have any current in it. Okay, because as you can see here, as this red starts going clockwise, So as this red is going clockwise, current's coming down here, and it's pushing it into either the blue phase or the green phase, depending on which one's the highest. Okay, because we have here, notice these peaks. Down here, they're showing you the peak. This is your IA peak, IB peak, and IC. So what you get is you always have one of them is coming down as another one is going up to its maximum. All right. And then as the third one starts going up to its maximum, then the other one was at its, and where these two are equal, where phase B and C here are equal, phase A is maxed out as negative. Okay. And so they're always pushing, so when A is the highest, it's pushing down this way, and it's going to push the current into either phase B and or phase C. So watch this. For a little while, it's pushing both the green and the blue. Okay. And so I don't know, it's just a really nice animation somebody did that demonstrates the current flows through a three-phase system. And you can see there how, we don't even need a ground wire. It's just the currents are passing back and forth through these three wires. Okay. And so three-phase is just very, very nice. We effectively can transmit 3 times the power. All right. So again, you can do this using a Y to delta, a delta to Y, or a Y to Y. Okay. It doesn't really matter how you're doing that, but you're going to see that now these slides are showing 1.73, which is that square root of 3. Okay. So if you remember, right, so that was the value. Who was that that first put that? Josh posted that, at 9:23. So over an hour ago, Josh told us that the square root of 3 was 1.73. Okay. And so that's why these slides have this 1.73. It's a square root of 3 in there. Okay. All right, so I'm just going to quickly go through a few of these slides here. A lot of these are kind of describing where that square root of 3 comes from. Okay. All right, so one thing that you're going to see here is this 208 volts. All right, so if you were to look, right, we know like in our house or whatever, we have 120 volts RMS. Okay, if you were to multiply that times this square root of 3, that gives you this 208 volts. Okay, so when you're talking about three-phase, you see people talking about 208 volts all the time. That's the line-to-line voltage. Okay, so 208 volts line-to-line is 120 volts for a single line. All right, another voltage that we see a lot in use is 480 volts. Okay, so and this kind of just goes back to the transformers we talked about last week. If you increase your voltage, you can transfer the same amount of power with less current. Less current means that your conductors are smaller and your amount of resistance in your loss due to the resistance in the wires is smaller because your actual current is smaller, right? Because remember, the loss, if we look at this circuit here, there's resistance in these wires. All right, so this box is like resistance in the wires, and that resistance in the wires is I squared R. Okay, so the loss of the power loss is I squared R. Sorry, I kind of said that incorrectly. Where's my subscript? Not seeing it here, but I squared R. Okay, so the power loss is I squared R. So if we go, using a transformer, if we step up our voltages and make those higher, then these losses get smaller. Okay. And so, a lot of these voltages that we see, a lot of times we'll see like 480 volts for electric motors and other big loads. Okay. And if that's not big enough, then they tend to make them even larger. So you see some of the motors run at like 1,000 volts or something. So you can reduce your current, but still get the same power. And you also reduce your loss in there. All right, so here's an example of a delta power supply or generator. So over here on this side, we've got this three-phase power generator piece over here. And then it's connected in parallel to a Y connected load. So it's connected to a Y and then a delta load. All right. And so, it's just a matter of, it's just like kind of, these are in parallel. So you pretty much just like treat one circuit and treat the next. Okay. So as I was saying earlier, typically when you were talking about these three-phase systems, you're wiring these things up to like power a three-phase motor or something along those lines. And so the circuits, when you take these loads like this, you just keep adding and adding, but you're adding in parallel. So you can just like calculate what is the power here, what is the power here, and the powers just add. Okay, because you're talking about how much energy is being used, and so they just add up. Okay, so you can look at what's the current flowing through here, what's the current flowing through here, and there. So so typically they're going to be like that. Now we're not going to get into unbalanced loads, but if the loads are unbalanced, then the circuits obviously get a lot more complicated. But again, you can always apply mesh analysis. You guys have gotten pretty good with the mesh analysis. All right, so some of what I've got in some of these other slides is just information talking about transmission. When you're transmitting these voltages or this power, when the hundreds and hundreds of miles, right, they build these big transmission line towers, and when you drive by, you see they got all the trees cut away, right? And so the reason for that is that with this thing being 115,000 volts, which is not really one of the highest, right? Some of them get up to like 500,000 volts, so almost 5 times as high as this, right? So when you're talking extremely high voltages, what happens, trees are made out of wood, which, a lot of times we think of wood as being an insulator. It doesn't conduct electricity. However, if you have 115,000 volts, you can get that to transfer. It'll flow through wood. Okay, at such a high voltage, you can get a current to flow through that wood. Now, so if a tree was to reach that wire, it would not short it out. It would act like another resistance, right? Because trees are wood, so they're not like metal. They're not conductors. They're more like insulators, but you can get current to flow through an insulator with a high enough voltage. And so what happens is it looks like another big resistor there. I mean, if you think about it, right? We talked back in DC that a lot of the resistors are made out of carbon, right? Well, what are trees made out of, right? They're carbon molecules. And so, there's a lot of carbon in the tree. So they're like great big resistors. And so if these wires get close enough that they act like another resistor attached to it. And so they don't actually necessarily just short out the circuit and blow the circuit breaker, but they actually just act like more load, people hooking up more load. And so when you look here, obviously, you're running wire from one tower to the next. Okay. And so, so this wire is going to hang down, obviously. But what happens is this is the wires in the winter time when it's really cold. They sag some, but they don't sag as much. But if you were to look at that same thing in the summertime, right, then it got longer for one thing, right? Because it's heating up. As metal heats up, it expands. And so it's gotten hotter, so it expanded, and so it's going to sag some more. And then the other piece, though, is what happens in the summertime when it's really hot. Everybody's running their air conditioners, all right? And those air conditioners draw a lot of current. And so you've got that current flowing through these. And remember that I just talked about that on the other slide, right? I squared R. The current is heating up the wire, right? The wire has resistance, and so it's changing that resistance within the wire to heat, which is making it even hotter. So it's kind of like a double gotcha. It's already hot because it's summertime. It's the hottest day of the year, and everybody in town's got their air conditioners on. And so they're drawing current through there, which is going to make it heat up even more. And so the wires are going to sag down even more. And so we need to make sure that those trees do not get up to the point where they get close, and that even if they're not actually touching, that you can get like sparking and arcing and going down through those trees, and they act like more load. So now you've got more load, which means more current, which means wires are heating up more. So I don't know if any of you remember, but I forget, I think it was 2003 where we had that massive blackout that took out, from, here in Ohio all the way up to, all the way over to New York and up into Canada. And, it was just this massive blackout because all the electric lines went down. And I've read a lot about that. They did studies and things and said, well, why did this go out? And part of the reason, it wasn't the entire reason, it wasn't the initial cause that started the blackout, but it exacerbated it because they found that there were areas where these transmission lines had not been cleaned out for a while, and trees had grown up to the point that with everything else happening, these lines got more current flowing through them, right? Because it was a hot day. It was in the summer, and so it was hot. People were running their air conditioning, and like I say, there were some other factors that actually caused a circuit to go down. But what happens is when one circuit goes down, the electric grid is connected everywhere, right? We're connected all the way up into Canada, down into Mexico, all the way to California. I mean, the grid's connected all together, and so what happens is if one line goes down, they do have circuit breakers on those different lines, and so if one line goes down, um, the rest of them have to try to take that slack up. All right, and so what happens is we had one line went down for whatever reason, which means that all the current that line was carrying ended up, because people were still trying to use the exact same amount of electricity, whether that transmission line was working or not. And so what happened is all that current got transferred over to these other lines that didn't go down. Well, then what happened? Well, another one went down because it started getting overloaded. And so we had this cascade effect. And, once two or three dropped out, now you have, two or three of these that are down, and yet we're still trying to transfer the load. So these other ones are trying to make up that load. And so, they get hotter and they drop down closer, and then they maybe find another tree to short out, which adds another load, and it just was a huge cascade that took out, I don't know how many states, and how many people lost power to that. Okay, so it was just a massive, uh, thing that just one thing led to another. Okay. All right, so this is just some slides talking about this power transmission stuff. Another thing to think about is, you've got all these power lines running hundreds and hundreds of miles, and you get, like, in the wintertime, you get ice on these. You get like an ice storm or something like that. So you see these big insulators here. That's just kind of showing what these kind of things sort of look like. So they're kind of built, you've got to have insulation in between here. You've got to have some insulation in between here. You can't have metal connecting to the metal tower, or you would just be shorting it out. Okay, so you've got to have this insulation here, but that's kind of what those look like in there when they build these things. Okay, this is a fun job here. I mean, these guys get to be way up here, and obviously you're not going to be up there with 500,000 volts or something on it, but you can. You got to do some maintenance on them once in a while and things like that. So, all right, just a couple other slides I'm going to hit here. Switch gear, and we have a whole class on switch gear, which depending on which program you're going through, you may be required to take it or not. But switch gear talks about, how do you got something coming into here. Like, where was it? One of these, okay, so like this one here, I guess it says it up here. I knew it said it somewhere, is 13.8 kV switchgear system here. And it's just kind of showing you, obviously, you don't want to be walking around and anywhere near 13 point, 13, almost 14,000 volts. And so, switch gear is the equipment and that's specifically designed so you can turn on and turn off these high voltage circuits. Okay. All right, so I was kind of looking, I have a I did have a video for showing like one of these high voltage circuit breakers for a transmission line going down. But I can't seem to locate it at the moment. Okay, so if I can find it, I'll post it up into Blackboard so you guys can watch it. But it's kind of a cool video showing the transformer or transmission line shutting down in here. But so you look here, like on this diagram here. Okay. Up here you see these bars. These are actually kind of like the circuit breaker. Here. Let me see if I can find this video because it's just very cool. Yeah, I'm not having much luck here. Okay, I think I found one anyhow. I don't know if this is the one that I had, but let me switch over. This is just very cool showing this circuit breaker breaking here. Okay. Oops. Wanted to replay it. All right, so this is just kind of showing what happens, like, that when we had that blackout, right? We just had this massive, all these breakers tripping because they had too much current flowing through them. So, you really need to, you got to have circuit breakers on there to prevent too much current running through those wires, because too much current, actually, if you remember, we discussed that last week when we were talking about transformers, I talked about that they are aluminum steel reinforced wires, these transmission lines. And aluminum, if you put too much current through it, will actually catch on fire and burn. All right. So if you were to shove, if you were to allow too much current to flow through those wires there, all that aluminum would end up literally burning away and be gone, and then they would have to re-strip those wires, right? So they have these circuit breakers. They have these circuit breakers here to open up, and that's that current trying to stop. That's see the as that thing's going through there, that's that current. That's current flowing through there, and it's flowing from one side to the other that whole time there. Okay, until it finally dissipates, and then there's no current. But while it's doing that, that's current flowing, and it's heating up the air. Okay. So anyhow, I just thought that was kind of a cool video I just share with you. Okay. So all right, so like I say, we're not going to get too detailed into this three-phase because we're pretty much out of time, but it's very important that you understand the the use of it, and the fact, because any factory, most any large business is going to have three-phase coming into it because it's just the most efficient way to 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 send that, because you can send, as I said, you can send 3 times the power that you can do with a single phase by adding one more wire. And so, and you don't have to have a ground. Now, your house connections only get one phase, and so they have to have a ground, all right, also. But those great big transmission lines like that don't have to, so when you look at these big transmission lines, they just have 3 wires on one side and 3 wires on the other side, because each one of those is a separate circuit. Okay. So the 3 wires on the left side is one circuit, the 3 wires on the right side is another circuit. Okay. And actually, if you see here, they got 2 wires running it, so might be the same circuit, or they might be actually 2 separate circuits, but most likely they're the same circuit, and they're just running 2 wires because of the amount of current that's got to flow through them. Right. There will be a little bit on there on the final, but not on exam 3. Okay, so exam 3, I'm not going to put that on there. I'm going to open up a homework a little bit later today. There'll be a 3-phase homework for you to do, and then there'll be maybe some of the questions out of that homework on the final, but there's not. I'm not going to put them on exam 3. Okay. Any other questions? All right. So, this 3-phase stuff is very cool. The biggest things to think about, I mean, as I said before, everything we've talked about all semester long applies, especially Ohm's law, Kirchhoff's voltage law, and all that. The biggest thing that we see with this is we can talk about either a line to neutral. Let me flip back to my drawings there for a minute. So we can talk about line to neutral or line to line. Okay. Okay, so we can talk about either, line to neutral or line to line, and they are square root of 3 um, difference in magnitude, and there's a 30-degree phase shift between them, depending on, which voltage you're looking at. Okay, so Andrew, sorry, Alex. When did you say exam 3 would be due? If you don't take it Wednesday, you got to have it completed by Sunday. Okay. So somewhere between Wednesday to Sunday. And then the final exam will open up on Sunday and will close by next Wednesday because I need to get grades done. So it'll have to be done by Wednesday. All right. So any other questions regarding anything? So yeah, we're pretty much done with the class here. So just got 2 exams and 1 homework, and the semester will be over. All right. So if you have not registered for the fall, you definitely want to be thinking about doing that. We're looking at a lot of different things, but we definitely expect to be back in the classroom. It might be a little bit different. What what exactly it'll look like as far as whether we have to wear masks. I don't know. Hopefully by then we won't have to wear masks or something, but I'm sure we'll still be kind of trying to be have more precautions in December or in the September or August, whenever classes start. But for the fall, but you definitely want to be thinking about either summer classes and or fall classes. We really don't have too many engineering classes being offered, but if you need to pick up one of your non-electrical classes or non-technical classes in the summer, but definitely think about for the fall, continuing on, unless you're graduating, which a couple of you might be those, but most of you probably still have quite a few classes to go if you're in AC this semester. So if you need any help with scheduling or anything like that, make sure you email me, talk to me. No, Andrew, there's actually the summer is broken up into 4 different paths. There's a 5-week session. There's a first 5-week session. There's a second 5-week session. There's the 8-week session, and then there's also a 10-week session in the summer. So they kind of offer different classes at different things. They're all definitely accelerated. And yeah, so it's definitely going to be probably a bit of a challenge to do calculus, and you're talking calc, not pre-calc, right? Is that correct? You're an AC now, so you already had pre-calc. So yeah, he's talking the calc class. That's yeah. The one good thing about it though is the fact that you're probably not taking 4 other classes, right? So that's the only class you're taking during that 5 weeks, or are you taking something else? Just the one. So the good news, I think, it's definitely accelerated, but at least you're concentrating on one topic. It's not like, oh, well, I've got an exam in calc today and I got an English paper due tomorrow, and you know what I mean? So so that's the plus side, I guess, right? There's always got to be something on the plus side. And so the fact that you're only concentrating on that one class over the summer. So, but yeah, 5 weeks for Calc 1, that will keep you busy. So I hope you're not planning on working too many hours to go along with that. Yes. Um, yeah. So yeah, if you're in one of the pre-engineering or whatever, and you got to take those other classes, because you need your physics requires Calc 2, I believe, as at least a co-rec, and and it affects everything. So, all right, but yeah, if any of you having any you know questions with scheduling or anything, shoot me an email and we can discuss it one-on-one. We can either do a collaborate or telephone or just through email, whatever you prefer. And so, but I hope to be seeing you all face to face in the fall. Uh, it's kind of a weird way to end the semester here, totally online, but all right. So, but yeah, so we're not quite done yet, though. We've got one homework and 2 exams, and then we'll be done with the class. So send me an email if you run into any issues.